I am the Vice President of Performance Services for Emerson. And I'll go through real quick and sort of introduce, maybe many of you guys have heard about who Emerson is, but, obviously we're a large, diversified company. But one of the main things that we do that impacts this conference is automation solutions. And so providing, valves and transmitters that we incorporate into our process to do measurements and to control that, as well as control systems and a number of innovative solutions that's there. Within that. So you can see as a global company, we have people all over in locations all over the world there for Emerson. We do have a focus on, sustainability, ESG, that's there. And so you can see a statement there from Mike Farr, and this has been presented in a couple of other presentations, but we're really trying to, utilize that control system, utilize those controls to really drive, profitability within the plant, but also sustainability and environmental compliance. And so controls is a great way to do that. And one of the pieces of my group that has a really big impact to that is advanced process controls, actually, that we can take and make sure that the material that's coming in, being processed in our facility, is being converted as efficiently as possible into end product, and we're not having off spec and other elements that would be there. Today, we're going to talk about flare controls. This is obviously the flare session. You guys have been talking about this, and you guys are experts in flare and the device that's there, how we remediate those gases as they go out towards the environment using that flare. In my background, I'll just briefly say I've worked in refining for a majority of my career in controls, so I have known the flare. I probably set it off a couple times with a mistake or two here, and so that does occur. And so I've been very familiar with that and worked with it over the years. And so we're going to be talking a little bit about the 40 CFR 63 part 670 and 671 as well today, and sort of some of the requirements for those. We've been seeing a number of implementations in the industry on different platforms, and we just sort of wanted to talk about that and then answer any questions at the end if there are any. So background, obviously this is very elementary for you guys, but the flare is used really to convert those hydrocarbons and other toxics or combustible compounds, into a compound that would be more acceptable for release into the environment, right? And so it is really trying to use combustion there to get that to something that is not as reactive in the environment or unacceptable to the people in and around the facility that's there. It's a critical system. Obviously, we're using it for pressure relief, right? So it has to be there anytime we have a piece of equipment operating within the facility. We need to have that flare system running, and so it needs to be operable. And so it is the first up and the last down, right? Always, whenever we're working around it, doesn't have much outage time. The flare system is required to handle a variable load and unexpected changes. I mean, by definition of a flare system, we understand, it's got a lot of material that might come towards it at any given time, and it might not have very much coming toward it at another time. And that is the sort of expected, unexpected life of the flare that's there. Historically, it's had few controls, right? We've sort of set it up and put it out there and, make sure it's going, and the operator might take a look at it, put some steam in it and do different things there. But largely it's been viewed as a device that performs its function, and it was largely manually controlled by simple inspection, right? That is there. And problems around it, right? I mean, obviously it's built as a safety device to handle that material that's coming towards it. But incomplete combustion is the number one, thing that you would see there, where you might have stuff that's coming at the flare and it might not be hot enough, or there might be too much material coming through at a given time, and it can actually lead to incomplete combustion. We can have heavy materials obviously move towards it, right, that would cause a smoky flare, and then we need to bring in dilution and other things to remedify that. Impacts, obviously there's the regulatory side of it, right? This is something that's monitored from an EPA standpoint, is if we're talking about in the United States. And so we have to answer questions and make sure that we stay in compliance from a regulatory issue. And then probably more importantly is community issues, right, around the facility. We are seeing that this is of increasing importance, that we maintain a good relationship with the community around us. And obviously when the flare goes off, right, you get the calls and everything occurs there. And so we just want to make sure that we're doing the right thing that's there. We're out with the community around us, and we release stuff that's fully combusted and ready for release. So something new has come out, not very new now. It's 2019, but you know, obviously with the pandemic and everything, we haven't had a chance to get together and discuss it as much as we'd like. But there's the CFR 63670 that's there, and it is the requirement. And you can see right in the title, right, for flare control devices. Some of you guys, I'm supposing most everybody's sort of aware of this, and it went into effect January 30th, 2019. That was there. It had a lot of requirements in there around the pilot presence was one of those things that was an important piece there. Visible emissions, it talks about that, and we got to control visible emissions, the smoke, smoky flare, that type deal. Flare tip velocity and maintaining flare tip velocity within a certain range. Maintaining operating parameters within the combustion zone and dilution there, and then obviously monitoring, right? This is something that's been real traditional, the monitoring piece there, but the control pieces that are all above that is relatively new to the industry, and probably provided your automation guy a lot of frustration if they were trying to implement that in the control system itself. There was a lot of calculation methods. It was very prescriptive, a lot of what they put out there on that. It was a lot of equations, very, very detail oriented. And then there was emergency provisions that were applied in there. So this is sort of a brief overview from a high level, just to remind us sort of what we're trying to comply with there. And then 671 mainly was around, it was mainly around quality records, right? Quality management documentation. And it really pointed back to 670 a lot on what was needed to be monitored in the regulation that's there. Pretty short, the 671, the 670 is a lot more detailed in that range. So what's the really upshot of the changes that we see there, right? It's really to treat the control, actively control the flare system, right? And help it to achieve its primary objective, right? Of what? Complete combustion, right? If you see with the velocity they're doing at the flare tip, the temperature, the net, you know, what they're doing with the heating value that's there, they're really looking to make sure that, hey, we completely combust the material that's going through the flare. That is really the objective of the legislation when you go through the whole thing and look at it, is really making sure that the flare achieves an objective and actively control it. Whereas before it was generally viewed as a passive device, now it's really viewed as an actively controlled device. So for me as a controls engineer in the past, I didn't have very many exciting controls on the flare many years ago. But today the world has changed. It's different in the United States now when it comes to flare controls. So we got to think about the problem. There's a couple issues when you say, hey, we're going to move to an actively controlled device there. One of the things is it's got to respond to immediate demand, and it's got to be always available, right? So we got to make sure that whatever controls we put there, that they're able to handle, you know, that immediate demand and that change in demand that can come. The biggest challenge, you know, me as a controls engineer, if you want to control something, you got to be able to measure it, right? And so that's a key thing. You have a lot of unknowns. Composition of the material. Well, what's relieving? Is it the heavy side stuff? You know, where's this coming from? Is it lighter material? Is it hydrogen? You know, is it what are the compounds that are coming at me? So that composition of material, depending on your facility, can be very variable depending on the size of it. With larger facility, you're going to see more variation there, and typically smaller facilities, you see a little bit less variation, although I have seen quite a few that can dump a lot of hydrogen into the flare, which causes a lot of issues, but you know, that's another thing. And then the amount of material, right? During certain operations, you might get a lot of material, and others that. So the controls have to be able to respond in a way that meets that. And we'll discuss a little bit later on, but it can also vary, you know, it's literally second to second on it. You have multiple objectives that need to be met in the regulation. You're trying to drive that net heating value. Everybody's pretty aware out of this regulation that we're trying to meet a minimum net heating value. That is one of the key elements of it, is get above that minimum net heating value. There's also a velocity at that flare tip that you're trying to control that's there. There's pilot presence and there's dilution. right? So there's multiple objectives that need to be met. And I'm not going to try to go into each one of these in detail and discuss the calculations. I think that everybody can understand that. I'm really trying to go from a standpoint of how does the controls need to be adjusted so that you can meet this? Because you can try to go code each one of these into a control system or go get a black box to do that. And what do you end up at the end of the day with that versus sort of the overall approach to how you can implement this into your control system. Unfortunately as well, when that demand comes for the flare, right, what's happened to our operations staff? Well, hopefully they're looking at the source of where that material is coming from and fixing that problem, right? So they don't have a whole lot of time to look at the flare, make adjustments and say, hey, do we got a smoky flare? They're probably not really that worried about it, right? They're really focused on, depending on how big the issue is, where the problem is occurring, right? And so the flare hopefully can take care of itself would be the ideal. And so the solution, I sort of was thinking through this and I was thinking, some of the aspects, some of the challenges that we come up with is what does that solution need to look like? Well, one, it needs to be always available, right? We've already discussed and we all know, hey, that flare needs to be there and it needs to be on demand. The solution has to be robust, right? It's got to be something that can handle a lot of the data demands that are thrown at it, right? Because there are times, just to be frank, with a lot of the measurements that we're trying to bring in at the flare, that they're not super reliable under certain conditions, depending on what's thrown at it. So we need a solution that can determine that and say, you know what, I'm going to disregard that reading. I'm going to use this value and use a computed value instead of that reading. So it really needs to be robust in that way. They have to be intelligent, right? It needs to determine, hey, we're in flare or we're not in flare. It needs to be able to respond to different modes of operation. Hey, we need, steam in the flare. We don't need steam in the flare, and it needs to do that. It needs to be able to run against all these objectives concurrently, right? It just can't focus on one thing and do another thing and do another thing. It really needs to be able to look at all the objectives. Hey, this is what we're trying to achieve, and go after all of them. And then finally, because that operator, right, they're busy, it really needs to be autonomous. It needs to take care of itself and do what it needs to do and really work reliably. So if you looked at that list and you go, hey, I got this, that you're pretty confident, because that's a pretty high list of demands, right? Intelligent, concurrent, autonomous, robust, right? Those are some big, and then I'll work always, right? So that's some big demands that are there. So, one of those things when you look at always available and robust, it really needs to be deterministic, right? We need an environment, an execution environment that those controls are running in that are very deterministic, that arrive at a goal, they're able to compute and get there in a deterministic manner. One of the things that we've learned over the years is it needs to be redundant, right? If there's a failure that occurs there, we need to have something else that picks up and runs, and that we have the capability to go repair that without it failing, right? If it's a simplex solution and it fails, guess what? Nobody knows until they're looking out there and they're going, hey, look, the flare's not doing what it should be doing, right? And we have some major issues. And unfortunately, that'll be during a time when, we're in an issue where it's escalated anyway. And it needs to be a system that's monitored, right? So we don't want something that is put off in the corner and nobody looks at till it's broken, right? Because then what's going to happen? We're only going to look at it when it's broken, right? So that's the challenge of those systems. We need something that's monitored, that's out there. And so, what we're looking at here is that I'm proposing that, one of the best places to put that is into your control system that's there. That is an ideal solution for that. And I'm showing you a couple of the solutions that Emerson has around this. And the first one is the Delta V PK controller. So we have a standalone controller, right? It's a reliable control environment. It's used to doing control. It's fully redundant, so if one of the processors had a problem or fails, or one of the IO has a problem, fails, right, it can shed to the next. And it's got a health status and it's consistent, right? It gives you a health score. You can go in, you can look on your Guardian dashboard and you can say, hey, my PK controller's looking good, and monthly you can see, hey, it's degrading, there's errors that are occurring, and it might not perform next time it's needed, or hey, it's got a great health score and everything is working well on it. That's there. And if you look over to further to the right, you have the Delta V integrated control system. And this is even better, right? Because now you're in front of the operator. It's continuously monitored. You have your board operator that's there. They're able to see in the system, and it's not a black box. They would get alarms. They would get other things if things start to go wrong with that solution. And you obviously have your automation staff that is monitoring it, and it reports its health rather successfully that's there. So it's a reliable control environment, fully redundant, and it's continuously monitored on top of that. So those are the things that we can see from the execution platform. It needs to be intelligent and concurrent, right? It needs to be able to detect that flare event that is occurring, right? So it needs to be able to see that material come into the flare and make sure that we're making the correct adjustments there. It's got to resolve the multiple constraints, right? So we talked about the flare tip velocity and the net heating value, and there's different things that you can do, a lot of inputs, and we're going to see on the next slide where we talk through that. There's a lot of different solutions to the problem. Right, you can sit there, we can adjust different handles and actually arrive at a valid solution, believe it or not. And so we don't want to approach it as a single variant problem. You want to approach it as a multivariate problem and make sure you end up with the optimal solution. Otherwise, we'll just be emitting additional greenhouse gases, other things that are not ideal. That are there. It needs to be able to handle computations that's there. And I put a little bit in the middle of an example of a constraint that we have programmed in the system. I pulled this out of our specification document. And it's just showing sort of the net heating value, making sure that, hey, when we're adding gas, right, that the heating value of the gas is over the heating value of what's being flared, right? Because it's not necessary to obviously supplement if you're over that. And so just showing one of the computations that's there. And then we might need to validate inputs versus one another. So, you can see over here, we have sort of some volumetric flow rates of those gases, right, that are coming through. Well, what if it's sort of bouncing in and out and we have a bad reading and different things that are occurring there? What happens to that calculation? Is it going to perform in a desired behavior, right? So we need to be able to validate those. And so basically what we built into the system is being able to understand, okay, this is bouncing around, this is sort of this value, and hold it at a given rate, right, that would be there. And so that's an important piece. So in some reasons, as I mentioned, you're able to have multiple handles that are used. I'm able to adjust steam, I'm able to adjust air, I'm able to do the nitrogen or purge, and I'm able to adjust the fuel gas and do some different things that are there and arrive at a solution. And then in other areas of the curve, right, I'm not able to do that, right? I get sort of limited. I can't do this, or I push the velocity up, or I'm dropping the heating value, and so you get limited. And everybody's sort of aware in here probably that, as I hit more constraints, that reduces my degrees of freedom, right? So it's a typical constraint control problem that's there. A lot of control engineers, where they go make a mistake here on the flare controls, is they try to treat it as a number of single variant problems. Right. Whereas when on our solution that we're doing, we're treating it as a multivariate problem with multiple constraints that's there. So we're able to adjust the variables and achieve the optimal goal that we're trying to get to. So release systems, just to remind, is like when you see the flare, I mean, you typically have something that's seating, unseating that can occur, right? So you can end up with a lot of oscillation within that, right? And so you can end up, and we've seen this happen numerous times in the flare controls, where your controls can sort of end up in no man's land. Right, because the inputs are oscillating to it, and it's trying to control this way and that way, and guess what? It ends up between the two poles that it's oscillating between, right? And so it ends up in this no man's land that's there, and you need to be able to resolve that. The system has to be intelligent enough to say, okay, I'm going to push it this direction and arrive at this solution that's there that's optimal. So just be aware of that. So bouncing and oscillation, it's a thing when it comes to flare. I mean, you look at it, you see it, we're all aware of that. So you can see the number of handles that's there. So I showed a typical makeup of a flare control system that's there. This one is sort of highlighting our GCs that Emerson has around the fast GCs that's there. And so, but you can see I've highlighted the purge and some of the supplemental gas and some of the steam. And you can see that there's multiple control elements because of the range that has to be addressed, right? Whenever we go in and we need to control this, we might need to have multiple valves so that we can address small, range of control or trim all the way to very large, right? And so you can see that even on the steam, there's two, on the fuel gas, there's two. And so you want to be able to handle those in a correct manner. Believe it or not, sometimes it can be difficult even for control engineers just to program these in a logical way that makes sense. There's good ways to do it, and there's not good ways to do it. And I would say that I've seen them all out in the field. that's there. And then you have some inputs that are coming here, around the flare gas and pilot gas. So you got to be able to read, detect, and understand what is occurring there. And you got to understand, hey, when these might begin to tell you a false reading, and when you might want to take and sort of bias it with a computed value instead. And so those are some of the things that we do. That's how we handle the balancing. That is also how we handle some of the regimes where we get into certain compositions where maybe our volumetric flow rates might be off. And so we correct for those. So you see a lot of adjusted values in the solution. So there's a lot of complexity that's there, and this is an example of an implementation that you can see that somebody's done, right? And you can see here we got some ladder looking logic, some flow logic that's there. And sometimes people try to use sequential logic to do this, right? They see complexity, they say, hey, I need to make a lot of decisions. Let me use a sequential function chart to solve this in. And there's some good things about that. Sequential function charts are really good at highly ordered operations. If I was making a peanut butter and jelly sandwich, a sequential function chart would be a great thing, right? Because I could go one step after next. In a typical way, many specifications are written that way, right? Because when I write stuff, it's linear, right? I write from the top to the bottom of the page. I present my ideas in a linear manner. And so a lot of people take and read the spec, and immediately they go to, hey, I want to use a sequential function chart for this. But one of the challenges with it is there's some cons to sequential function charts, right? It's executing one action at a time, one after another. They're highly ordered. That's there. They can become stuck, right? I got to look at the logic. Got to be real careful. Okay, in this condition, when I'm executing this step, what are my abnormal situation handlers? How do I move out of this step, et cetera? And so it is really built for type logic. That's what those sequential function charts, when we made them for the control system, they were in response to S88, a batch protocol that was there that was put forward. They're not really well suited for driving multiple constraints like what we talked about in the flare controls. And they're not as responsive to change, right? They weren't built to be on-demand type response modules in the control system. They were really built to be something that directed a recipe, that drove a given process that would be there. So it wasn't really built for that. So there's some big cons to the sequential chart that's there. So what would we do otherwise, right? Well, if we don't do sequential function chart, what else is out there that we might be able to do? Well, I'm going to introduce a concept around what's called state-based control. And so there's a whole ISA around this, ISA 106, that's there. And so that's something that it's a new development that's out there. It's actually been in industry for a very long time. It was actually invented many years ago, before the computer even existed. But the states are defined, from process knowledge. So we have a number of defined states that are there. And so for our example, with flare controls, we might have the flare being offline. We might have it in low flare mode. We might have it in a high flare mode. We might put it in manual mode, right? So it can definitely recognize those different states that are there. And you can think of a simple thing like a lock on a door, right? That door can be locked or unlocked. That would be the two states of that lock on your door. Exact same way with the state engine, is it has a very simple logic to say, hey, what mode of operation are we in? The process is always in one state, right? The flare can't be in low flare or high flare at the same time. They're discrete states that would be there. Each state has its own configured actions, right? So it would know exactly what to do and how it would configure those controls, interlocks, et cetera, in each mode of operation. And then you have smooth controlled movement between the states. So if it needs to go from low flare to high flare, that it's able to transition very effectively from that and even into offline mode. And I would say these transitions that you see here between these can be automatic transitions or manual only or both, right? So you could very much say, for instance, going offline, right? That would be something that potentially an operator would have to do. You'd say, hey, I'm going to take this from low flare, I'm going to shut this off, bring it into offline mode, or bring it back into low flare mode that would be there. So how we approach this, right, is this in our smart process solutions business that we use. And we have a number of different applications that's in there. What we do is we have a specification document that we have that is sort of written around the whole legislation that's there, really covers all the aspects of it. And we have a team that would get together and will work with your controls group or you and go through that specification, get it built for your particular flare that you would have there. People have different applications that's there. They have different needs for their given facility. And so they typically build that specification. for that. It's a pre-written flare. It's a template, right? A pre-written template that's there, and so you go through and you update it for the needs of there. And then what we do is we implement that as a standard solution in typically our PK controller that I was showing you earlier. That's there. And so what you do is you get a standard solution without a black box, right? It's something that you can maintain on your control system. You can merge it into any control system, or it can be native on the Delta V system that would be there if you have a Delta V system. And so those smart process solutions are a great way to go. We do them for a number of different applications. Flare is one of those. We have smart process compressor, which is a little bit larger application for turbines and compressors. We have SRU applications for sulfur recovery units that was there, and actually it was actually one of the first ones that we did. Heater as well as blending applications that would be there. So you might have some of those others that might be relevant to what you're trying to do. So just these are my contacts that's there. So I just wanted to pass that along to you. Do you guys have any questions sort of about the solution of what we're proposing there? Oh, that was pretty quick. Anybody has a controls background or mainly environmental? Mostly environmental.
Sequential chart.
You can program a sequential function chart like a state engine. In fact, the sequential function chart by SA88 is defined as a state engine itself, believe it or not. It's a little bit difficult though, but because how it's built, it's a little bit difficult to do that within the sequential function chart. In Delta V, we actually have a block called the state transition diagram that is built for state-based. So.
Sorry, I missed the beginning of the talk, so maybe spoke about it.
Sure.
So what is the ROI on these systems?
The ROI, like, well, I mean, typically what you're looking at is it would be, you know, what are you having as far as non-compliance? Like if you want to look at, you know, hey, I'm getting, you know, X amount of non-compliance fines, et cetera, deviations that would be there around that. And also the fuel gas savings, right? So you can see massive amounts of fuel gas savings because you're driving it towards an optimal thing. Because a lot of times what we see in solutions, let me sort of say one of the reasons why we sort of got looking at this is that we saw a lot of implementations of flare control systems out there in industry. And to be frank, when we started digging into some of them, we realized they weren't actually doing what they were actually programmed to do. We could see the intent of the legislation. We looked at the system and go, this is not doing what we think it should be doing, right? It's either, you know, had a lot of manual values typed in there, and we're like, man, what in the world's going on here? You know, we're wasting fuel gas, we're doing all this type of stuff. We're thinking, man, we can save a lot on this, pulling the fuel gas back and really getting it optimal. So the ROI typically depends on the size of flare, but you know, it depends on how much fuel gas you're using, and then non-compliance. Those are the two areas that you need to look at for it, and it's going to depend on your facility, obviously, for that. But it's actually pretty significant on a lot of places. So. But good question. So we've seen a lot of people struggle. There's a relationship there between, I'm just being real honest, right? Between the environmental department and the controls department, right? These guys trying to implement this in the control system, and you know, they might get a document from you guys that has, you know, something like this in it, right? And they're like, oh, what in the world is that? You know, hey, I just need this in my control system. And they're like, I have no idea what you're talking about, you know, and it can be a little bit of a challenge that's there. And then when it gets to the readings, right, the measurements of what we're talking about to implement this, it can be a challenge. And to be truthful, what we think is happening there is that the controls automation department is just eventually going, man, we can't get this measurement tied in. It's really struggling. You know, we can't, you know, it's not accurate. And I've spent hours upon hours of this, and I can't just spend any more. So we're just going to type this in and say it's working. Right, and it's a tough deal that's there, but that was one of the reasons why we said, hey, this can be done in a lot better way that's there. And it's a big struggle, because if you go piece by piece, single variant, it's really difficult to get to the solution. But if you look at it as a holistic solution and say, okay, this is really what it takes to get to work, and you can tune that in. There's a number of tuning parameters, by the way, behind this to really tune it in for the flare. Then that's really what makes it go. So good question. All right. Well, if you have any questions or something comes up later, or you talk to your automation department, then please, feel free to share contact info with them. We'd be happy to talk about a solution with them, and always come by, visit us at the booth that's there. I think that's finishing up here pretty quick, but visit us booth. We'd be happy to discuss anything with you. All right. Thanks, everyone.